G'day, Michael here. This is the second video in a series of demonstration of how to take measurements and produce suitable sketches - drawings for maybe designing your kitchen or any other environment. I might even try and cover some staircase measurement, that kind of thing. But in any case, here I am with my rough beard and a sheet of raw MDF. I'm going to produce a kind of a small simulation of various environments, rather than it's near impossible for me to take you to all the sites I've been to show you the sorts of things that can be done or can be needed to be done. But I want to give you some insight into how to take measurements in complicated environments, not just your simple rectangular space. But having said that, there are issues with the rectangular spaces which I aim to alert you to pitfalls, things that can catch you out when you're measuring a square space. Anyhow, less than me, more of the subject. Here we go. Alright, so for this simulation, this represents a alcove for a wardrobe, and this would be a wall continuing on this way, and this wall would continue on continuously this way off, the width of a room, whatever it takes. Okay, so this is a space for a wardrobe. Now I'm doing these deliberately as a sort of a scale model, just to make it a manageable size. You can see what I'm doing at the same time as the simulation. And of course, I can simulate anything where it's near impossible for me to take you to every site that I've been to that would be of interest. Now I've drawn in here and I've highlighted some common deviations from what the expectation is. This represents the wall. Okay, so this is my open space, and we're going to put a wardrobe in this space here. Okay, so what I've done here is this wall is out of square deliberately. This one is square, but it's got the common variations that you have with stopping. Now with a gyprock or a dry wall, a rendered wall, any sort of wall finishing internally, you'll end up with a filling in the corner so that it is not a square, a completely square set corner. It will actually have some sort of rounded fill-in space. And of course here's another internal corner. But on an external corner, particularly on the plasterboard wall or gyprock wall, you end up with a small piece of metal that protects the corner, and then a filler that sort of blends it back into the surfaces. Right, so this end here, in effect, curves. I'm kind of going to generate a curve to simulate that kind of a curving effect. Now this side here is at an angle to start with, going off, but it's also got this filler in the corner. Now, our temptation is, on site you don't necessarily see this. I've exaggerated it so you can see this clearly here, so this is kind of a cheat sheet. But in the real world, this is just a smooth flat wall, this is just a smooth flat wall, it all looks square. So even measuring a square space can be quite problematic. If we can get an understanding of what sorts of traps there are even in a square space, other more complex spaces will help. It'll help you understand those as well. Okay, so if I went along and say measured what looks like a fair thing, I'll jam the tape measure up here and here, and I measure, say, 564. So I'll just write that down here. 564. I know it's upside down to you, but maybe I'll invert the video later. See how we go. Alright, now this part here is, I'm going to call that 570. So in the middle here we've got 570. Now on the front, that's how we get there, is also 570. So the expectation is, okay, 570, let's make the unit a little bit narrower. I don't know, 568 will certainly go in. That's your first thought. Well, okay, let's try that. Let's assume we've just made a cabinet 570. So I'll use red for the cabinet. There we go. So red simulates the maximum width we can make a cabinet in this space, and it'll be probably somewhere here you'd end up finishing it. And as you can see, there's quite a difference here. And believe it or not, that's not an uncommon difference between what's planned and what's possible. Okay, so from this red line to this red line, I have 550. So we have from 570, apparently, only 550 available to put a square box into. Now that may surprise you, but that is a common deviation from what the expected, could be. Not only that, when we have a square space, we might have a hump or a hollow in the wall. So this wall may not be as straight as I marked it initially here. There might actually be a lump, maybe a crooked stud in there, or just variations that happen in a building site. So we measure the depth over here. I think, oh yeah, we've got 177 millimetres over here. So depth here was 177 possible. Okay, so that looks fair enough. Now let's just do some okay, so I'm going to do exactly what I did a minute ago and convert this to a what's possible type line. And in a length of wall, it's not uncommon to have that much of a bow in it. So again, we thought we had 177. Now what do we actually have? We've got 160, I'm going to call it 166 millimetres. So what we ended up with was 166. So hence you can see the need for having, that's 11 millimetres difference. So we've got minus 11 here, and well, in this axis I should do that. So we have basically 11 millimetres shortfall here, and on this, what did we say we had? We said 550, didn't we? Yeah, 550. So we had expected 570 as a possible by measuring, say, the front or the middle, but what we ended up with was 550. So somewhere we've lost 20 millimetres, and of course, because you can see it here, you can say, oh, that's where it went and that's where it went. But in the real world, you don't have that option. You just see what appears to be a square painted wall. So these are the sorts of tricks to, the sorts of tricks that the wall can play on you. It appears to be a nice square, perfect wall, but you end up with variations. Well, okay, how do we measure this? What do we do to make sure we don't have these problems? Well, there's a couple of things you can do. One of them is to have a straight edge. Now, when I say a straight edge, if you had something that was longer than the space or substantially longer, a substantial length of the space, you could in fact lay the straight edge down. I might just slide that along. I've just extended my room out, so I've got some floor space here to work with. I scratched around the building site and I found a random piece of timber. Now this might be 5 metres long, or a bit of, a flooring joist or something. You have to look down the eye. Now if you were to look down this piece here, I'll just sight that up so you can see how straight that is. If I put that there, you can see by looking down the edge there how straight that is or isn't. You see that? Now you can see there's quite a curve vertically, but horizontally, this way, it's pretty good. So there's a curve this way, but that way it's pretty straight. So I'm using that as my straight edge. So you can use that to examine a plank or a piece of aluminium or whatever's kicking around the building site to find something straight that's long enough. And then you can lay that down somewhere. They're usually going to weigh something, and you can measure. Okay, this is our wall. This particular dimension here to my plank is, say, 200 and I'll make it 220, so I've got a consistent space. So I'll make this side 220, and that side also is now 220. So I could go along and look for any bumps. So that's 210. So that's telling me already, comparing to my plank, that we've got a 10 millimetre variation. And so my temptation is to throw another 5 millimetres in there just as a tolerance, because there'll be other variations The walls will also not be plumb. You can use the spirit level to measure how plumb the walls are, but basically the conditions are the same as going across. There'll be all sorts of reasons for the verticals to vary as much as the horizontals vary. So it's worthwhile keeping an eye out for any of those deviations you see. Okay, so that's one way of establishing a straight line. Another way, you can use the laser. Now the laser is great because it allows us to set two planes at a right angle to each other. So if I was to use the laser and go, okay, that's 200 and... I might set it at the 350 mark. So I'd set that, actually I might move that further back. So I'll set this up so both ends are saying 350 at the deepest. So that's pretty good. Both tape measures are reading 350, which means I can go along and try the wall in various places. Okay, there's a bump there. Okay, that's measuring 340. So we've got the same story being told whether we use the laser or the straight edge. So there's two possible methods of assessing the flatness of a wall. Now, as for testing something for square, there's a couple of different ways you can do it, but there is all sorts of scope for variations and tricks being played on you. But a good method, and the Egyptians were the first to use this method that I'm aware of. They didn't know quite why, well, many believe they didn't know quite why, but they used a 3, 4, 5 triangle. Now if you need to learn about Pythagoras, that's somewhere else. But anyhow, what they would do, they discovered, I'll just maybe draw it up here, they discovered by whatever means that if you have a triangle that is 3 units long one side, for another side, the hypotenuse is by whatever means 5. Now visualization I use to explain this to like students and whatnot. So demonstrate this being a set of squares. Now 3, 4, 5 is a handy number to use because they're quite an equal number, and it doesn't matter what kind of unit you use. If you remember 3, 4 and 5, you've got yourself a measuring tool for square. I'm just putting this little demonstration here of how 3, 4, 5 might visualise in your head. 3 squares by 3 squares is 9 in total. 4 squares by 4 squares is 16 in total. 5 squares by 5 squares is 25. Okay, 9 plus 16 equals 25. That's Pythagoras' theorem, kind of explained in a I don't know, a picture. I hope that zoom out slightly. Okay, so here we have 3 squares by 3 squares makes 9 squares. 4 squares by 4 squares makes 16 squares. 5 by 5 is 25. 9 plus 16 equals 25. So by whatever means, if you have access to the diagonal and one side, you can assess the third side. If you've got access to either of the square sides, you've got given the hypotenuse. Okay, so how do we apply that here? Okay, well this is about, I might just choose 150 millimeters. So it's, in my case, this is a whiteboard marker, in my case, I'm going to choose 50 millimeters as my base unit. Okay, so that would be from there to there, 150 millimeters, or 3 lots of 50. And from this way, we'll do 4 lots of 50, which is 1, 2, 3, 4. Now what's our diagonal? It should be 25 centimetres or 250 millimetres, and it isn't. It's a much greater distance. it's 273 millimeters. So it should be 250, so we end up with 273. Now all of these measurements, you're not aiming to perfect the building site, you're aiming to collect enough information to make a facsimile of that you can replicate where you're going to do the manufacture. Or if you're going to use a CAD program, you want to be able to create a good facsimile in the CAD system of the site. Then you can actually build the design of whatever's going to fit in that space. So I've shown you methods and traps. I suppose the next thing is, how do we record that? What do we need to do? What do we need to write down so that we can find what it is we're looking for? Okay, so I would grab a piece of paper. I'm going to do this as clumsy and as broadly as I can. I normally use an A4 sheet, but for the point of having this video clear, I'm just using A3 and I'm using these big fat markers to demonstrate what we've got. Okay, so what is it? Blue. There we go. I draw just freehand. The fact I know that's out of square, so I would alert myself by saying that that's out of square, and I'll draw something like that. A little bit of a simulation of what I understand the space to be, and we can write down there our 3 measurements. If you like, you can do that. If you've been able to generate a square line, which we can do with the laser, or we could do with Pythagoras, we could create this square line out from that back edge. That's an alternative way. In fact, I might demonstrate that too before I get too carried away. Okay, so going back to our Pythagoras trick here. So we're using 50 millimeters as our base unit in this case. So coming out 200 millimeters, going diagonally 250. We could make a mark like that, and then from that point there, we'd mark out 150. Now, here you can see the problem I have. We're actually creating a right angle. Okay, so by doing my little 3, 4, 5 triangle here, I ended up creating a triangle in this location. I'll do that in blue so it's clear. It's actually quite good that this worked out this way. So there's our 4 side of the triangle. Then I produced this arc of the 5 side, which in my case is 250 millimeters by 200. Now we come out from that same point, 150, which is 3 times our 50 millimeters, and it gave me a point over here. But as you can see, what that's done is, even though I think I've made a square line, I've made it square to this portion. I haven't made it square to the whole line. So it becomes very tricky to assess on site what actually is square. You've got to make sure you're taking enough information in. Now there are other numbers you can use that really bump this out. Now, okay, if you grab, I don't know how much of this will be absorbed or rememberable by you. I'll grab a piece of paper, maybe. We already know, by this example, 3, 4, 5 as an example. Okay. The next whole number example is 5, 12, 13. The next whole number example is 7, 24, 25. You can go up. I mean, this will be starting to get impractical because your ability to measure will start throwing deviations in. But I will show you how to achieve that. You go up in, not prime numbers, in odd numbers. So 1, 3, 5, 1, which doesn't work, 3, 5, 7 and 9. Okay, now the rule is 3 by 3 is 9. Divided by 2 is 4.5, right? The two numbers you have here are the 4, which is smaller than 4.5, and the 5, which is larger than 4.5. So that's how we achieve those two. Next one, 5 fives are 25. Divided by 2. It's 12.5. Okay. Take away the half, we've got 12. Add the half, 13. So here you can see those two numbers are here. Same thing here, 7. 7 sevens are 49. Okay, 49 divided by 2 is 24.5. Take away 0.5 is 24. Plus 0.5 is 25. So, on this one, 9 times 9 is 81. Half of that is 40.5. So our other two numbers are 40 and 41. So if you can remember the rule, you can recalculate your own. But these ones are the common ones to remember. Now, can we apply, say, that one in our example here? We had, I don't know, that dimension there was 564, so say 550. Well, that's a bit of a nuisance. What would be the next size down? Okay, so if we were to use 40 millimetres as our base unit in this case, so 40 millimetres, and we're using the 5, 12, 13 example. Where are we? If we use 40 millimetres as our base number, 12 times 40 is 480, so I can use that same point now. 480 is to here. So, is to here. Okay. Now we use this point here, which is what appears to be the corner. 480. 5 fours are 20, so it'll be 200 millimetres. Which should be just off the page here. And a diagonal, 13 times 4 is 520. So 520 over that length is out to about here. So we still have the problem, although we're getting closer, we still have the problem as that it's referring to a dodgy source. But it is closer to our original square line than the smaller reference. So as you can see, they are methods you can use to establish a square line on an otherwise unknown space with a humble tape measure and something to mark with, and your brain. So they're the tools I needed to establish that, and so that's how we can establish a square line. The easier way, of course, is to have this bit of kit where you can, in fact, I'll turn it the other way, you could set the laser so that it is parallel, using the method before. 280. Okay, and then you have something to refer to. You can measure theirs, for argument's sake, what is that, to that corner, 60 millimetres, and to there is 75. So the laser is established in that same space. So if you have one of these tools, life's a lot easier. If you don't have these tools, you can use this method with the various triangles and a tape measure and your tool to mark with to establish a square, or you can simply build in ample tolerance, like guess that 10 millimetres is the gap, and so we're going to allow, say, 20 just to make sure it's safe. So they're the three real options. Either measure it well, so you know your numbers precisely, but if you've got the tolerance, just use the tolerance and create tolerance to make life easier. If you've got a piece of equipment such as this, that can make life a lot easier for assessing a site. And that is the big reason why I've got this guy, because it establishes a right angle and another right angle, and they're two vertical planes, so they give me a lot of information. And of course, if I need a horizontal, I fire up the horizontal plane where it's gone. I don't know if you can see that, probably not. You can see on my hand there, that's a horizontal plane being established. See, it will tell me how the floor varies. Now I'll use that as an example by standing back here. I might put it on the other side. So I've just got, can you see that? Yes. That's showing 100mm or 101 there. And over here, the same. Of course, this little space on the workbench doesn't show up much. But if there was a variation in the floor of 10mm, it would show up with the laser. So a tool like this laser is very handy, but they are expensive. Everyone has got a tape measure if they're doing any work. Something to write with, something to write on, and a brain. So these methods that I've shown here are methods for handling with limited resources. If you've got the ability to get hold of a laser, buy one, own one, or borrow one, or rent one for that matter. I don't know whether they're rentable. But in any case, these sorts of pieces of equipment can save you a lot of time and really bump up the precision. And of course, the easiest way out is to build in a lot of tolerance into your design, like having an infill panel either side that will give you 20 or 30mm space, or in depth, make sure the cabinet's much shallower. So, okay, so coming back to what I was starting to draw, here's the facsimile that I'm making of the space, one that I can carry home. Note that it's not the same size as that. It doesn't even have to be accurate to scale, although if you've got a scale grid paper, it can help you to be reminded of the things you see if you have got a referring rectangle scale behind it. Okay, so I've drawn roughly the angle that I see, the wonkies I believe I saw. I overlooked the back one because I couldn't see it, for argument's sake, but that's okay. And I'm going to use the measurements I've got here. I measured 177, so I'm going to write down that measurement there as 177, even though it's errored. Okay, it's important that I make note of that. 177. It is errored. I haven't been able to assess the 166 because I was careless and I didn't spot that bump in the wall. It was invisible to me. But what I will have is the cabinet itself is going to be designed to be 150 because of how I naturally work. Okay, the width there is 570. Oh, sorry, here was 570 at half depth and the front edge was 570. But I did go through the process of assessing that wasn't square. Either way, it was telling me there's some fishy business over here. So I'm going to build in a 30mm infill on this side. And the same there. Just because I saw, even with my little Pythagoras method, it alerted me to the fact that there was an error here. So I might make a note, 30 infill. No, terrible. A 30 infill. And I'm going to put, as a dimension there, nonetheless, I'm going to put the 570, which is what I could measure. Because I've got the infill here to denote what I've got to worry about. I tend to draw a highlighted detail of the corners having, stopping in them. Because you will, if you look, once you're alert to that fact, you will look in the corner and go, oh yeah, there is a bit of stopping there. That is a bit rounded. But at first glance, if you're not aware of it, you may overlook it. That's why I've made this simulation as best I could. Alright, so I've got 570, and I'm going to call the depth of the cabinet only 150 is what we're going to make the cabinet. Okay, so that's the intention. Now what I'll draw also for the customer is a bit of a perspective, which I always find is a very handy thing, and it's also very handy for me too. I'll draw what I perceive is the space. Now there may also be something like a light fitting coming out of the ceiling. And so there might be obstructions to be seen. In any case, these dimensions are not useful dimensions for a cabinet. I would be making a cabinet typically 4 times the size of this, but I'll just use these real numbers because they're just numbers. Okay, so I've got 150 deep, and it might be, I don't know, maybe a bulkhead above. kick below, infills, and they might, I don't know, one set of 4 doors or something like that. So they've got some sort of handle on what it looks like, and I've got some sort of handle as to what I'm seeing in the room. There's a light fitting here. It's going to have 4 doors, and it's got this wall coming off to one side. Of course, if you wanted to take photos, you could do that as well. But in any case, there's our information. That's our intended design. That's the facsimile of the width and depth. The height, I'm just going to throw in that it's a ceiling height of say 2400. But again, because I've got the, going back to the original design here, we have a bulkhead on the top side, we have a kick on the floor, and they might be both normally 100 millimeters or 4 inches or something like that, depending on where you're from and what measurements you take. I might even have this as 150. That gives me some tolerance to work around the ceiling and floor errors and so forth. But in width, that's fairly tight. I'm only leaving a 30 millimeter infill. Let's see if I can write upside down. Wow. Weird. Okay, so we've got a 30 millimeter infill either side. So that's that drawn in. And the height, I might either mark on here, I might mark the dimensions this way on the drawing, depending on what I needed to do. But if I've got the information here, that's fine. And what I would tend to do is put like the ceiling height, 2400 or whatever the height would be. And I might also measure the height in a few places. Depends what I see on the site. But in any case, I think that's enough for our first video of actually measuring a site and the sorts of traps we can get with a right angle. In future videos, I intend to do curved walls and angular walls and so forth. And we'll see how we go from there. Well, that was a bit of a marathon. It was a lot more complicated than I thought it was going to be. But there's a lot of insight you need into measuring a site. And I hope this covers most of the traps you'll tend to fall into with measuring even a square site. Later on, I intend to cover things like curved walls, angular walls, and maybe staircase environments too. They are fairly tricky to measure. But first things first, we'll get this design understood. My next video will actually, maybe we'll draw something from this, maybe use a CAD program or something to get the facsimile of the space into something we can handle. Okay, well that's it for me. Hope that's a bit of interest to you. Feel free to like, share, subscribe, make a comment, ask a question, a suggestion for another video, or if you want something perhaps focused on another video, let me know. Well, that's it from me. Bye for now.